Hi everyone, this talk is called Stochastic Linear Bandits Robust to Adversarial Attacks. I'm Jonathan Scarlett, and this is a joint work with Ilya Bogunovich, Arpan Lasalka, and Andreas Krauser. First, I'll show you the standard linear bandit setup. This is where we have a usual bandit problem, but with linear rewards. So the reward is an inner product of an unknown vector theta with the action that you take A. And we may also be subject to Gaussian or sub-Gaussian noise, which is this epsilon t. We consider a slightly less conventional problem where we additionally have adversarial corruptions, meaning that in addition to the random noise, we're also subject to adversarial noise. We consider a very powerful adversary that knows the underlying problem, including theta, and even knows that the action that was taken and that it's corrupting. But we want to constrain the adversary in some way, so we assume that the total sum of corruptions cannot exceed some parameter, which we denote by C. We use the usual measure of cumulative regret, which is the sum of suboptimalities between the chosen action and the best possible action. Our first main result gives a regret bound in the case that C is known to the algorithm, and our regret bound decomposes into an uncorrupted term and a corrupted term. The algorithm builds on a recent approach known as phased elimination, based on eliminating suboptimal arms, but we have some important changes to tackle the robustness, including enlarged confidence bounds, robust estimation, and a certain truncation technique. The uncorrupted regret term is already known to be optimal from previous work. And regarding the corruption term, we can also show that omega C dependence cannot be avoided using a very simple argument. We then extend this result to the case that C is unknown, and we get a very similar regret bound, but with an extra C squared term. Our algorithmic approach is again similar, but we can't use C, so instead we keep track of a tolerated corruption level which decreases over time. The C squared term may look a lot larger, but we also show that it's in a sense unavoidable, or at least that if you want to avoid it, you need to increase your uncorrupted regret significantly. So if you insist on optimal uncorrupted regret, you basically can't avoid the C squared term. Finally, we move to a slightly different setting where instead of a fixed action set, we have a different set of actions or contexts given to us every round. This was studied in an earlier work where it was shown that perhaps surprisingly, a very simple greedy algorithm can provably succeed under a certain context diversity assumption. Our third main contribution is to show that under the same context diversity assumption, we also have robustness in that we get the previously known cumulative regret bound plus an order C log t term. Okay, so I won't go into details on that, but our paper is on arXiv if you'd like to know more. Thank you.